Hello my dear students, I warmly welcome you to CR Digital Classes. So now in this lecture, we are going to discussing about one of the important topic, orthogonal set is linear independent. In the previous lecture, we discussed that the definition of orthogonal set, orthogonal basis and the inner product, outer product, length of the vector, normalizer. So all these definitions we discussed in the previous lecture. So now in this lecture, we are going to discussing about orthogonal set. Whatever we discussed in the previous lecture, that orthogonal set is linearly independent, or the vectors in orthogonal set are linearly independent vectors. So we have to prove that condition. In this lecture we have three problems. So all three problems related to orthogonal set, and the vectors in orthogonal set are linearly independent. So observe the statement first of all. First question, if capital S is equal to u1, u2 up to so on u suffix p is an orthogonal set of non-zero vectors in Rn. Okay, so there is one orthogonal set. Orthogonal set, that means by hearing that word you can understand that if you take any two vectors, for those two vectors the product value equal to 0. Orthogonal set itself is nothing but the any two different vectors product value equal to 0, not same vectors, any product of any two different vectors equal to 0, then those vectors set is called orthogonal set. So that type of set is capital S we have here. Now we have to show that capital S is linearly independent set. That means we have to prove here u1, u suffix 2, u suffix 3 up to so on u suffix p vectors are there, column vectors. Those all vectors equal have linear independent vectors, and we have to prove. Next, second problem, let u1, u2 up to so u suffix p be an orthogonal basis for a subspace W of Rn. For each small y in W, the weights in the linear combination small y is equal to c1 u1 plus c2 u2 plus up to so on c suffix p u suffix p are given by c suffix j is equal to y into u suffix j by u suffix j into u suffix j for j is equal to 1 to up to so on p. Okay, the second question tells that whenever you take an orthogonal basis, set is different, basis is different. Okay, so in question number 1 we have orthogonal set. In question number 2 we have orthogonal basis. Set that u1, u2 up to some u suffix p be an orthogonal basis in a subspace W of a vector space Rn. Then for each vector small y in subspace W, there is one linear combination. For that capital Y, there is one linear combination. That linear combination is c1 u1 plus c2 u2 up to some cp up. You know very well where c1 c2 up to some c suffix n's. Okay, c1 c2 up to some c suffix n are the weights. Before linear combination they are called as a scalars. After linear combination we can call them as a weights. Okay, weights. So those weights have some equation. Those weights also have some equation. That equation is c suffix j is equal to y into u suffix j by u suffix j into u suffix j for all j is equal to 1 to so on p. అంటే ఇక్కడ సెకండ్ ప్రాబ్లం లో ఆ స్కేలార్ వాల్యూస్ కూడా మనం ఫార్ములా ఫైండ్ అవుట్ చేస్తున్నాం. ఆ స్కేలార్ వాల్యూస్ ఏమంటాం మనం వెయిట్స్ అని చెప్తాం. ఆ వెయిట్స్ కూడా ఫార్ములాని డిరైవ్ చేస్తున్నాం whenever in an orthogonal basis. Third problem, the set capital S is equal to u1, u2, u3, okay, where u1 is equal to 3 1 1, u2 is equal to minus 2 1 and u3 is equal to minus 1 by 2 minus 2 7 by 2 is an orthogonal basis in R cube or R3. Express the vector y equal to 6 1 minus 8 as a linear combination of vectors in capital S. Okay, express this vector as a linear combination of the vectors in capital S. So first question related to second question. Second question is related to the example for the third question. So with this lecture we will get the clarity on orthogonal basis, orthogonal set and the weights formula. First of all we are going to discussing about the given set is orthogonal set and that is linearly independent. Given set capital S is equal to u1, u2 up to some u suffix p is an orthogonal set of non-zero vectors. Later, whenever you take set of vectors, then we can take the linear combination. Let C1 u1 plus C2 u2 plus C3 u3 plus up to some C suffix p u suffix p equal to 0 be a linear combination where C1 C2 up to some C suffix p are any scalars. Okay, so then we are taking that the product property. Why? Because we are taking that first vector u suffix 1, with that vector we are taking that entire linear property or linear combination multiplication. Why? Because to show that this entire set is linear independent, we have to prove that each and every vector, okay, has all zero scalars. Ikkada mana concept entante, we have to show at the end of this problem, we have to show C1 is equal to 0, C2 is equal to 0 up to so on C suffix p equal to 0. Then only we can say that set is linearly independent. At least one scalar from C1, C2, C suffix p not is equal to 0, then the given set is linearly dependent. If all scalars equal to 0, then the given set is said to be linearly independent. That is our aim. So to show that, so we have considered one linear combination amma C1 u1, C2 u2 up to so on Cp up equal to 0. With that linear combination, first of all I am taking the first vector of the set capital S, okay, that is orthogonal condition. Clearly that set is orthogonal set kada. So orthogonal set lo unna vectors em cheyali, that product inner product value equal to 0 avvali. So therefore C1 u1 plus C2 u2 plus up to so on Cp up into u1 equal to 0 into u1, or else we are multiplying on both sides with small u1 for this equation. Now multiplying with C1 u1 for each and every term in that linear combination, then you will get C1 u1 into u suffix 1 plus C2 u2 into u suffix 1 plus up to so on C suffix p u suffix p into u suffix 1 equal to 0 from the properties of the inner products. So therefore from the third properties of the inner product we can separate that value, scalar value we can write outside. So then C1 into u1 into u1, okay, we can make that we can apply that bracket for these two values, plus C2 into, from this term C2 into u2 into u1 plus up to so on C suffix p into u suffix p into u suffix 1 is equal to 0. Okay, since u suffix 1 is orthogonal to u suffix 2, u suffix 3 up to so on u suffix p. Why? Because clearly we are taking that set u1 u2 up to so on u suffix p is orthogonal set. Orthogonal set means each and every vector forms that orthogonal condition with respect to every vector. If you take first vector u suffix 1, that first vector forms the orthogonal condition the remaining vectors. Okay, so therefore since u1 is orthogonal to u2, u3 up to some u suffix p, according to that orthogonal definition we can write u suffix 2 into, why? Because here u suffix 1 is the fixed, just we are taking that fixed vector, that vector is orthogonal to remaining vectors. Remaining vectors are u suffix 2, u suffix 3, u suffix p. U suffix 1 is a fixed vector here, therefore u suffix 2 into u suffix 1 is equal to 0, u suffix 3 into u suffix 1 is equal to 0, therefore u suffix p into u suffix 1 is equal to 0 according to that orthogonal vectors definition. Then substitute these values, substitute these values in this equation. Okay, substitute those values in this equation. Substitute these values in this equation, then you will get C1 into u1 into u1, we don't have any value. So why? Because u1 is not orthogonal to u1, so that's why we are writing u1 into u1. Okay, from this value, so we are writing that value C1 into u1 into u1. From this value C2 into, so you can write C2 into something into 0, 0 directly, and next here C suffix p is there, this value will become 0, so that's value we are writing here 0. Directly I am writing that value. Okay, so therefore C1 u1 into u1 plus 0 plus up to so on 0 is equal to and RHS also we have 0. 0 into U1 0. So therefore LHS we remain only C1 into U1 equal to 0. Okay. So here this product is vector. That vector is not is equal to 0. Why? Because U1 is a vector, amma, that vector is always not is equal to 0. From the properties of inner products condition, whenever you take U1 into U1 equal to 0 only, then you will get U1 is equal to 0. But here U1 is a vector, that is orthogonal vector, that means it is a non-zero vector. That's why definitely then C1 will become 0. Therefore then C1 will become 0. Since U1 not is equal to 0, therefore U1 into U1 also not is equal to 0. So C1 is equal to 0 and what is that C1, amma? The first weight in that linear combination. Next, similarly, if you take that the linear combination with respect to U2, okay, so we have C1 U1 plus C2 U2 plus up to so on, C suffix P U suffix P is there. For that linear combination, we will apply that orthogonal condition with respect to U2, then 0 into U2, you will get this condition. Again, by applying that properties, you will get C1 into U1 U2, okay, plus C2 into U2 into U2 plus up to so on, C suffix P into U suffix P into U2 equal to 0. Okay, so clearly here U2 is orthogonal to remaining vectors in capital S. Remaining vectors ante U1, U3 up to so on U suffix P. That means this value will become 0. This value not is equal to 0 and this value will become 0. So therefore then you will get only, okay, so you will get only C2 into U2 equal to 0. All values will become 0 except the second term C2 value. Here U suffix 2 not is equal to 0. Why? Because it is a vector. Then automatically C suffix 2 equal to 0. Then the scalar constant value should become 0. C suffix 2 equal to 0. That is only here we are writing that value. That is only here we are writing that C suffix 2 equal to 0. That's why similarly we can get that process C suffix 2 equal to 0. That means if you proceed in this format. Okay. Next, if you take C3 in place of C suffix 2, if you take C suffix 3, then U suffix 3 in place of U suffix 1, if you take U suffix 3, again you will get C suffix 3 equal to 0. In place of U suffix 1, if you take U suffix P, then you will get C suffix P equal to 0. So here C suffix 1, C suffix 2, C suffix 3, C suffix 4, all are the weights, okay, are scalars. All scalars are 0. Then the given set, whenever all scalars are 0 in the linear combination, then that set is linear independent set. Okay, therefore capital S is equal to U1, U2 up to some U suffix P is a linearly independent set, and it is a basis for the subspace spanned by capital S. It is a basis for the subspace spanned by capital S. This is the total proof of the first problem. Just we did nothing, amma. So we have to take the given set. Orthogonal set అని తీసుకున్నాం కాబట్టి ఆర్థోగోనల్ సెట్ అంటే డెఫినెట్ గా అక్కడ ఉన్న వెక్టర్స్ ఒక లీనియర్ కాంబినేషన్ ని ఫామ్ చేస్తాయి. సో దట్ లీనియర్ కాంబినేషన్ we are letting. After letting that linear combination, we are considering the first vector U suffix 1. ఆ ఫస్ట్ వెక్టర్ కి ఆ లీనియర్ కాంబినేషన్ కి ఆర్థోగోనల్ కండిషన్ ని అప్లై చేస్తున్నాం. That means inner product value equal to 0. So in that format, if you proceed that condition, see we got C1 is equal to 0. C1 is equal to 0 అని వచ్చింది. Similar గా in place of C1, if you substitute in place of U suffix 1, if you substitute U suffix 2 in that linear combination and orthogonal condition, then you will get C suffix 2 equal to 0. Similarly, C suffix 3 equal to 0. So C suffix P equal to 0. All scalars equal to ante linear independent అని చెప్పేస్తాం. With this, the orthogonal set is linearly independent.